Hello guys, and welcome to my video about the transformer. Welcome to my channel. First of all, I will be sharing, I hope every week, videos about AI and AI models. And this video in particular I made about the transformer, which is a very famous model which came out in 2017 paper called Attention is All You Need. I think most of you are already familiar with it, but if you're here it's because you want to have a deep understanding of this model. Because in this video we will go through every single part of what makes a transformer. I guarantee that if you follow all the video you will have a complete mastery of all the models. But of course I cannot go through every single detail, so there are some things that I take for granted. For example, I take for granted that you have a basic understanding of neural network, and I take for granted that you know what is a fully connected layer, for example, and some matrix multiplication. So let's start with this journey. And here we are talking about the transformer. So I think you have probably seen this picture also on the real paper and also on the internet. But before we talk about the transformer, let's make a step back and let's talk about why we need a transformer. So before we had the transformer model, we had these recurrent neural networks. What are these networks? Well, these networks are sequence-to-sequence networks. For example, imagine you have a sequence of X words. We can also say words. Okay, usually this kind of network I draw is actually not for machine translation, but we could say that we have a word-to-word network. So we have n words X, and we want the network to learn the mapping between this sequence and the Y sequence. So what did we do before? We started with our first input, that is the first item of the sequence, x1, this one here. We fed it to the neural network along with the initial state, which is usually array of zero, a matrix of zeros, and the network produced an output, y1, along with the hidden, it's called the hidden state of the neural network, of this recurrent neural network. Then to generate the next token, we feed the x2 token along with the previous hidden state to the recurrent neural network, and the network produces the y2 token. And this happens at time step 2. So in order to map n x tokens to n y tokens, we need n time steps. So it's like we are doing a for loop in which every time we reuse the hidden state of the previous loop, of the previous iteration, to create the next output. This has some problems and some limitation. Even if recurrent neural networks are still used in some scenarios, they are, however, not good for very long sequences, and we will see why. First of all, it's very slow to compute for long sequences. So if you have n tokens, input tokens, and you want to map to n output tokens, you need to do n iterations of this through the network. So for inference, and unfortunately also for training. And we will see in the transformer this problem has been solved. So, and the second problem is the recurrent neural network cannot be parallelized. So because every time we need the previous output, we cannot make it in parallel. So we cannot give him all the tokens at once and run the calculation in parallel, because anyway we need the previous output. We have the problem of the vanishing or exploding gradients. What does it mean? When we have a neural network, we have usually a loss function. Actually, not usually, we always have a loss function. And what we do is we do back propagation. What the back propagation does, it computes the partial derivative of the loss function with respect to each weight and updates these weights accordingly. Now, if this, let's say, this partial derivative, this increment that we give is very small, and because of the chain rule, we multiply all these, these gradients together. If we have a number that is between 0 and 1, for example, and we multiply that number by another number that is between 0 and 1, not an x, this is a 1, we get a result that is an even smaller number. And if we get a number, suppose we get a number that is between 1 and 1 or infinity, and then we multiply by another number that is between 1 and infinity, we will get a number that is bigger than both of them. So the gradients will either explode or vanish. And this is not good because in one case the neural network will not train because the gradient will move very slowly. The weights will move very slowly. Difficulty in accessing information from long time ago. And this is actually related also to the vanishing or exploding gradients. Basically, in the previous case, in the recurrent neural network, when we compute the yn, the information about the x1 is nearly gone, the longer the network is. And this is a problem because in language modeling, we want to be able to map also long-term relationships between words, because we may have a very long text in which one particular sentence depends on maybe a sentence that was 300 words before. And with recurrent neural network, this becomes very hard. Now, the transformer model was revolutionary because it solved all these problems of the recurrent neural network, or at least most of them, and it did it in a very simple way. What I will do here, I will show first the encoder and secondly the decoder. So this part on the left, this one, it's called the encoder of the transformer, and it's made by many layers, and the right part is called the decoder. I want you to be familiar with how to read this kind of diagram. I think it's quite self-explanatory, but maybe some of you are not familiar with it. So basically we will have inputs, which is a matrix. Then it becomes an input, it goes through this layer, input embedding. Then we add another matrix to all of these layers called positional encoding. The output of this layer is it's duplicated into 4 copies. One copy will go here, and this is called the skip connection into this layer, and 3 copies will go in this layer, multi-head attention. And the output of the multi-head attention is here, will be fed to this add and norm layer along with the skip connection, so along with the input that we fed here, and it will produce a new output that will be duplicated. 1 copy will go here and 1 copy will go here. Okay, so I want you to understand that this is actually duplication. It's not like we are splitting, we're just taking this input and feeding it into multiple layers. We also see a number here, nx. This nx means that this block here, which I highlight in green, is repeated n times on top of the other. So the output of the first block is fed to another block that looks like the same block. And the output of this, if we have n more than 1, will go to the decoder actually. And the decoder also can have multiple blocks like this. So here we have the decoder block, this one, and we have n copies of this, one on top of the other, and the last output of the last will be fed to this linear layer, which will then we will apply softmax and the output probabilities. I hope this is clear because we will be going through each part of this diagram. I want you to also familiarize with some notations that I will be using. The first one is the input matrix. We are building we will be dealing with a translation task. So we have a sentence, let's say in English, and we want to translate that sentence into another language, let's say in Italian. Suppose we have 6 words in this sentence. So what we will do, we will build a matrix that looks like this, which has our sequence length is 6, and we will also have an embedding size of 512. Now, what is the embedding? I will show later, but for now, you just need to know that each word is represented by a vector that is 512 dimension long. So we will have 6 rows in this matrix, and each row is actually a vector of 512 items. So from 1 to 512, and from 1 to love you very, for example, very much, right? This is our sentence. So each word is actually a vector, 512 dimensions long. And we have 6 of these vectors, and this is our input sequence, right? I will not be using this particular sentence. This is just to make an example. The next thing I want you to be familiar with is the matrix multiplication. So this matrix is 6 by 512. If we multiply this by another matrix, let's say the transpose of this one, so it's a matrix where we have vectors that are long, 512 dimensions long, 512, etc., and we have 6 of them. If we do this matrix multiplication, so 512 by 6, the inner dimensions cancel out, and we get another matrix that is 6 by 6. Okay, later we will see what does this matrix mean. Actually, I just want you to know that a matrix that is 6 by 512 or n by m multiplied by the transpose give you the outer dimensions, and not actually only in this case, but in every case. And okay, let's move on. Let's focus on the encoder first. So the encoder, as I showed you before, is the left side of the diagram of the encoder of the transformer, and we start with the input embedding. What is an input embedding? First of all, we have a sentence. Imagine we have a sentence that is 6 words long. Your cat is a lovely cat. We split this sentence into words called tokens, and we also have a vocabulary that contains all the possible words that our model can work with. And this vocabulary will have one position for each of the words. So we will have, for example, the word your will be in the position 105 in the vocabulary. The word cat, maybe it's in the position 6587 in the vocabulary. And these are called input IDs. So for each word, we find the position of the word in the vocabulary. The next thing we do is we create a layer that maps these numbers to a vector of size 512. This vector we will call embedding, right? So this vector is 512 dimensions, and this we will call embedding. So our word, each of our word will be represented by a vector. And as we can see also here, cat, this cat here and this cat here have the same embedding, okay? They have the same values in this vector. For future slides, we also define this quantity, the model is equal to 512, which is the size of the embedding vector for each word. Let's see what happens at the positional encoding layer. What is positional encoding? We want each of the words that we feed to this transformer to carry some information about its position in the sentence. Because when we constructed the matrix, the input matrix, we want each word to be represented by a vector. But this vector doesn't carry any information about where that particular word is in the sentence. So we need to add this information, and we do this through positional encoding. We also want this positional encoding to teach the model to treat words that are close to each other as close and words that are far apart from each other as distant. And we want the positional encoding to represent a pattern that a model can learn. For example, for us humans, when we see a sentence like, let's say, or I love you, we know that this word is far from this word, at least compared to this one, right? It's relatively far compared to this one. It's the distance between this word and this one is 2, and between this one and this one is 1. But the neural network cannot know this, so we need to tell him about this. How to do this? We take this sentence, we convert into an embedding, which we did in the previous layer, and we add a new vector to this embedding. So dimension by dimension, we add a new vector that tells that this particular word is in this particular position. Now, this embedding vector here only depends on the position, not on the word to which it is applied. So if we have another sentence that has another word here, we will add the same position embedding. So this position embedding only depends on the position, not on the word to which it is applied. After we add this vector, we will get a new vector that we will be feeding to the encoder. And as you can see, the size of the output vector is still 512, so we didn't change the size of the vector. You may have seen on the paper these two formulas on how to calculate the positional encoding. Let's see how to do it. So imagine we have this sentence, your cat is, so only 3 words. What we do is we calculate, we create a vector of size 512, which is the dimension of our embedding. And for the even positions, we apply this formula, the sign, and for the odd positions, we apply the second one. And as you can see, the values in this vector only depend on the position. So the pos, this parameter pos, indicates the position of the word inside the sentence, while the I indicates the dimension on the vector. So this is I equals 0, I equal 1, I equal 2, I equal... And for the cat, we will have this, and for the last word, we will have this one. I also want you to notice that if we had a different sentence, they would have the exact same positional encoding, because they don't depend on the word, but only on the position, which also means that we can pre-compute these positional encodings once and then reuse it for every sentence that our model will see. We don't need to recalculate it for every time we feed a sentence for inferencing or for training. One interesting thing is, why did the authors use trigonometric functions like cos and sin? This is because these two functions actually naturally represent a pattern that the model can recognize as continuously changing. So relative positions are easier to see for the model. And as we can see, I mean, when we as humans, we watch the plot of these two functions, this is a plot in which it's plotted by position, so the pos parameter that we saw in the previous page, and the depth, that is the I parameter we saw in the previous page. We can see a clear pattern here, right? And we hope that the model will also learn pattern when he sees these embeddings augmented with the positional encoding. Okay, we have seen how the input is fed, how it becomes an input embedding. First it becomes input IDs, then it becomes embedding vectors. Then we saw how to add the positional encoding vector. Now let's go to the next part, which is the interesting part, the multi-head attention. I will actually first show not the multi-head attention, I will show the self-attention without being a multi-head, and later we will see the multi-head. So what is self-attention? Self-attention allows the model to relate words to each other, right? To find some relationship between words. And you may be probably familiar with this formula that you have seen on the paper, but also on the internet. It's become very popular. Let's see what is it and how it works in a specific case. In this simple case, we will consider a sequence length of 6 and an embedding size of 512. The metrics Q, K, and V, which stands for query, keys, and values, are just the input sentence. Because in this case I'm only considering one head, we can consider this dk to be equal to the d model, which is the embedding size, and this Q, K, and V to be just our input sentence, that is a matrix that is 6 by 512. So this is our Q, which is 6 by 512. We multiply by the transpose of KT, which is 512 by 6. We divide by the matrix, the dimension of the embedding, apply softmax, and this is what we get. How to interpret this? We get an output matrix that is 6 by 6, so only the blue area of the matrix, the rest is actually only for showing you what it means. Now this is an example where I generated these values randomly, so don't pay too much attention about the values, but look at what higher level. This matrix represents this matrix that is the output of the softmax, and before it is multiplied by V, so it's actually, we are talking about this particular matrix. So before it gets multiplied by V, represents the relationship of each word with each other. What do I mean by relationship? You may have heard that actually self-attention involves some kind of dot product, right? So when you do this matrix multiplication, actually you are doing a dot product of each word with every other word. And the dot product is a way that the self-attention can work. So it is a value that multiplies corresponding dimensions of the embedding, sums them up, and And then we apply softmax. Softmax basically makes every value between 0 and 1, and also in such a way that they all sum to 1. So this particular row, for example, sums to 1, and this one also sums to 1, etc. This matrix represents every interaction of this word, for example, your, with all the other words. For example, we have this word cat, and we have the dot product of the cat with your, dot product of the cat with itself, dot product of the cat with is, etc. We applied softmax to it. And self-attention will try to learn the interactions of these words with each other using this dot product. Now that we have this matrix, we multiply it by V. V is also another matrix that is just an input, the input sequence, so it's 6 by 512. So if we do this multiplication 6 by 6 multiplied by a matrix of 6 by 512, we get a new matrix that is 6 by 512. And it's interesting to see that this dimension is exactly the same as the input sequence that we gave to this attention. This basically means that we have a matrix that is 6 rows, and each row is actually an embedding, not the embedding that we built before, but an embedding that includes the embedding that we built initially, plus the positional encoding, plus also captures some information about the interaction of each word of that particular word with all the other words. Okay, so this output of the attention is a matrix that is representing an embedding, a special embedding that captures all this stuff. So it captures the meaning of the word, which is given by the embedding that we built initially, plus the position of the word in the sentence, which is given by the positional encoding. And then now it also encapsulates some kind of relationship with the interactions with the other words in the sentence. Let's go through some properties of self-attention and why it's so important and actually so easy. First of all, self-attention is permutation invariant. Self-attention requires no parameter. I mean, up to now, we only multiplied the input sequence, the input sentence by itself, with the transposed version of the same matrix. Actually, we will see later that in the multi-head attention, we will have also some parameters. But for now, the interaction between words has been driven only by the embedding and the positional encoding. And we expect values along the diagonal to be highest. Why? Because the dot product of the vector with itself is usually the highest. And there is another interesting characteristic of this matrix is that if we don't want some positions, so for example, if we don't want the word your to interact with the word cat, because this is the result of a softmax, these numbers are the result of a softmax, we can actually, before we apply the softmax, if we delete this value and we put minus infinity, the softmax will output 0 at this position. So we can remove some interaction if we don't want them. And this will be used in the decoder, we will see later when we talk about the masked self-attention. So for now, you just need to understand that self-attention is a way for us to relate words to each other by doing this matrix multiplication. You may also have seen on the paper, but also on the internet, that these matrices are called query keys and values. And it looks like that this terminology comes from the database terminology or the Python-like dictionaries. I also want to give a little interpretation of my own. So imagine we have a Python dictionary or a database also that has a mapping between keys and values. So imagine we have a keys representing a genre of a movie and the values representing the movie itself. So for example, Titanic is romantic, The Dark Knight is action, etc., etc. Imagine we have a user that makes a query. The query is love. Now we could search the word love, we will not find it in the queries. But because we are in the transformer word, this word love will actually be embedding. It's a vector of dimension 512. And also each of these keys will be a vector of dimension 512. What the self-attention does, it calculates some values. So it calculates the dot product between this word and all the other words. And the result of the dot products will amplify some of the values and not amplify others. That the self-attention things could be related to each other. So maybe our self-attention head could think that the word love and romantic are very related to each other, so it will amplify the value Titanic. And it may also think that the value love and comedy are related, but maybe less than romantic, so it will also amplify a little bit the comedy, but maybe not amplify at all the horror. Now let's talk about multi-head attention. Don't be scared by the formulas. I will show you exactly with the diagram how each part of the calculation is done. And these formulas come from the paper. Basically, the idea is that before we had a single head attention before when I show. In this case, we will have more than one head, and I will show you what it means to have more than one head and why we need more than one head. We are in the encoder side of the transformer, and basically we had our input sentence. We transformed the input sentence into input embedding. We added the positional encoding, and now we are exactly here at the entrance of the multi-head attention. As you can see, this input is split into 4 parts. One, not split, it's copied into, it's duplicated 4 times. This one copy goes here, but we will not care about this copy. We will care about these 3. 1, 2, and 3. Let's have a look. We have our input to this multi-head attention, which is a sequence by D model. And what does it mean? We have a sequence, let's say a sequence of 10 words. And the D model is the size of the embedding. So we have a matrix that is 10 by 512. We make 3 copies of this matrix. One we call Q, one we will call K, and one V, which stands for query, keys, and values. Of course, they have the same dimension as the initial matrix because they are copies. And now we will introduce 3 new matrices. Let's call them WQ, WK, and WV, which will be multiplied by this Q, K, and V. These 3 matrices are parameters, right? They are parameters that the model will try to learn. And their dimension is D model by D model. So in our case, 512 by 512. The result of this matrix multiplication is a new matrix prime, K prime, and V prime of this dimension, so sequence by D model. Instead of calculating the attention using these 3 matrices, we will split them. Why? Because before in the previous slides, we calculated the attention using directly the Q, the K, and the V. But now we will get a smaller version of these matrices, and we split them along the embedding dimension. So not along the sequence dimension, but along the embedding dimension, which means that we will calculate, in this case we have 4 heads, so we will calculate 4 attentions using a part of the embedding of each word. This means basically that each head will see all the words, but for each word we'll see a part of its embedding, which in other words also means that each head will see the full sentence, but different aspect of each word. And each head will learn to relate the words to each other using different aspects of the same words. So this is the formula from the paper. So basically what we do is we calculate the attention between K1, K1, and V1 now, which will, the output will be this matrix, head 1. This is the output of the first head. This is the output of the second head, third, and fourth. And what we do later is also written on the paper. We concat all these outputs of these heads together. We obtain a new matrix. You can see the dimensions here. The only thing I want you to notice is that here we have a dV. What is dV? Before we had a dk. Now dV and dk are actually the same value. Here you can see the legend. And the fact that this one is called dV is because the last multiplication is done with the matrix V. But dV is actually equal to dk. Then when we combine them together, this matrix, the new matrix is sequenced by h multiplied by the dV, where h is the number of heads. So we have 4 heads multiplied by dV actually gives us D model. The result of this concatenation is multiplied by a new matrix called WO, and this is the result is the output of the multi-head attention. Also, in this case, I want you to notice that the output of the multi-head attention is a matrix whose dimension, whose size, whose shape is sequenced by the model. This basically means that we still have a sequence of words and we still have some embeddings, and now our embeddings also encapsulate not only the meaning of each word which is given by the embedding, not only the position which was given by this positional encoding, but also the interaction with the all words with each other thanks to the multi-head attention. Another thing interesting is that you may want to visualize the attention, because also in the paper they show that the attention can be visualized, and this is very powerful thing because we can understand how each head relate words to each other. This is done using an intermediate calculation, which I skipped here, but I will show you now. So when we calculate the softmax of Q multiplied by the KT and divided by the dk here, this results in a matrix that exactly the same like the one we saw before, so like this, which is a matrix of sequence by sequence, in which we can see a score. This score tells how intense is the relationship between that word and another word. And this attention can be visualized. This is a picture I took from the paper, from Attention is All You Need. And we can see that here we have a word making, which is related to other words, but by different heads and in different ways. For example, the word making is related to the word difficult by many heads, but only one head. So this pink head here related it to the word 2009, because maybe this head here could not see that part of the embedding of the word 2009 that allowed this other head to relate these two words together. So each head will see all the words, but each head will see a part of the embedding. So this head will only see 1/4 of the embedding of the word, and this head will also see another 1/4, and this one also another 1/4, and this one also another 1/4. And this is the idea behind the multi-head attention. Now that we have seen the multi-head attention and how it is calculated, let's go to the next layer, which is the add and norm. Now I will concentrate on what is the layer normalization and how it is used in the transformer and why it is important. So what is layer normalization? Normalization, okay, suppose we have a batch of 3 items, and item 1, item 2, item 3, and let's say the dimension of this vector. So this is a vector of the features of this item. Let's say it has a dimension of 128, okay, 128 features. What we do basically is we calculate the average and the variance of item 1 of all these values. We do the same for the item 2, and we do the same for the item 3, and then we normalize each value using its own mean and standard deviation. If this is the batch direction, so this is the batch dimension, okay, and this is the feature dimension, we are actually normalizing using the feature dimension, right, along the feature dimension, along this dimension. So each item is treated separately, they don't mix with each other, right? We also actually introduced 2 parameters. One is called gamma and one is beta. Gamma is multiplied and beta is additive, to introduce some fluctuations in this data, in this normalized data, because this normalized data actually is distributed between 0 and 1. But maybe these 0 and 1 are too restrictive for the network to learn something meaningful. So sometimes the network may want to amplify these values. And by introducing these 2 parameters, learnable by the model, gamma and beta, actually the model can learn to multiply each of these values by some other value, by gamma or by adding beta, when it wants to amplify one of them. I found this very nice visualization from paperswithcode.com, which shows the difference between batch normalization and layer normalization. So on batch normalization, we are normalizing one feature from each item in the batch, while on the layer normalization, we are treating each data item separately. So we never mix values from multiple data items. Let's have a look now at the decoder. First, let's have an overview of how it works. I will show later how to build this output shifted right when we will talk about inference and training of the transformer model. The output embedding and the positional encoding are exactly the same as the encoder. The only difference being that we may have two different vocabularies. So imagine we are doing a machine translation. We may have one dictionary for the output and one dictionary for the input because because they may be different languages. So one is Italian, one is English. We may have different vocabularies. And we have another difference here, which is the masked multi-head attention, while the rest of the layers are actually the same as the encoder. So the multi-head attention is exactly the same as the encoder. The only thing that is different is the input. So instead of taking the same input and copying it 3 times as a query key and values, we take the query and the keys from the output of the encoder. So here we imagine there is an encoder, right? It will give some output. And the values are taken from the previous output of the decoder. Okay, and these two layers, the linear layer and the softmax, we will see later when we talk about inference and training. So what is masked multi-head attention? Our goal actually is to make the model causal. It means that the output at a certain position can only depend on the words on the previous positions. So we want the model to not be able to see future words. For example, we don't want the word your, which is the first word in our sentence, to have any relationship with future words. We don't want it to have any relationship with cat, any relationship with is a lovely cat, right? And just like we don't want this one to interact, this one. Only the last word of the sentence can be related to all the previous words. But up to here, we cannot relate this one. So this means basically that each word can only be related to all the words that come before that particular word or the word itself. Which in other words also means that we want everything that is above this diagonal to be cancelled out. How can we cancel out these values? Let's see here. This is the decoder. Here we can see that we don't want all these values above the diagonal to be we want them to be 0, right? How do we do that? When we calculate the attention, so the Q multiplied by the KT divided by the square root of the dk. Basically, before we apply the softmax, we replace all these values above the diagonal by -infinity. Then we apply the softmax, and the softmax will take care of making them 0. Because the softmax, as you remember, is actually e to the power of x. So if you put x is equal to -infinity, e of -infinity will go to 0. Let's talk about inference and training of a transformer model. Now that you have all the basic building blocks of the transformer, I want you to see how they all work together, right? So let's first talk about inference. Suppose we have an English sentence, I love you very much, and we want to translate this sentence into Italian, which becomes ti amo molto. Let's start with an overview of our model, which is here. So we have our input, which is in English. I love you very much. What we do, we as we can see from the picture here, we first convert the input into input embeddings. So basically vectors of size 512 for each word. Then we add the positional encoding to each of these vectors. And finally, we send it to the multi-head attention. So we expect now to send this one to create the encoder input and send it to the encoder. The encoder will produce an output. What is the output of the encoder is another matrix that is sequenced by D model. Because as we saw before, the output of the multi-head attention is sequenced by D model. So it's basically the same as the input sentence, which means, in other words, that each embedding output from the encoder is not just a regular embedding, the one that we have here, because this particular embedding only captures the meaning of the word, but not the word's interaction with other words. The embedding that is output from here also captures the positional encoding because we added it here, but also the interaction with every word with other words, which was added by the multi-head attention. So we take this encoder output, then we want to have an output, right? So what we will do is we give to the input of the decoder, we will give the SOS, which is the start of sentence. It's a particular token that tells the model to start outputting something. These two sentences, even if they don't have the same length, because okay, it's for clarification, I mean, it's very easy to visualize them as what we actually want. Actually, what will happen inside the code is that we will have a fixed sequence length, let's say 2000 tokens. So the model will append to this SOS 1999 tokens that are padding. And to this sentence in English, it will append enough padding characters, tokens, to reach the 2000 sequence length. I'm not doing it here, of course, because it's not easy to visualize otherwise. But we have to think that these two sequences they have the same length. Okay, so we feed this sequence to the decoder, which will be fed along with the output of the encoder. Okay, so what I'm showing you here is this particular part here. Okay, we had the input, we fed it to the multi-head attention, and we also fed the query and the keys from the output of the encoder. Now this will produce some output, which is the decoder output, and this will be fed to a linear layer. What is the linear layer doing? The job of the linear layer actually is to map from because the output of the decoder, so this part, this block here, this big block here, let me highlight it. All right, this big block here, the output of this, which is here, is a matrix of the size sequence to D model. What we want, actually, we want to map each of these embedding to a vocabulary, to our vocabulary, because we want to understand which word this matrix, this embedding corresponds in our vocabulary. And this is the job of the linear layer. The output of this layer is also commonly known as logits. Then we apply the softmax. The softmax will allow us to choose one word among all the words in the vocabulary. And we expect, if everything is working fine, to have the first output word, which is T. Sentence "I love you very much" maps to Italian "ti amo molto." So we expect the first word to be T. And surprise, surprise, this happens at time step 1. So if you remember, initially we talked about the recurrent neural network, and we said that the transformer actually will not require n time steps, right? But actually this happens during the training, not during the inference. During the inference, we still need n time steps. Why? Because the model cannot know how to say, because later we will see that there are many different strategies of choosing the token. We can choose the next token using greedy or beam search. We need n time steps for the inference. At time step 2, what we do is we still have the same input English sentence, but we don't need to recompute the encoder part, because actually it's the same as before, right? I mean, nothing changes. Our sentence is still "I love you very much." So the output of the encoder, because we are doing inference, will be the same. So we can reuse the output from the last time step. We append the last output word, so T, to our decoder input. And then we build the input for the decoder block, and we feed it along with the encoder output from the last step, which I remind you, we didn't recompute again. We can reuse the previous one. This again will create an output, and we map it to a linear layer, and then softmax, and now it will produce the next word, which is amo. And this happens at time step 2. Time step 3, same thing. We added the previous output word to our input of the decoder, and then it will produce another word, molto. We do it again for time step 4. And finally, it should output EOS, which means end of sentence. So if everything is working fine, our transformer should work like this, if it has been trained correctly. When we do the inference, we are actually using a greedy strategy in the past few slides. That is, at every time step, we choose the word with the highest softmax score. But we don't have to only proceed in this way, and usually this way of proceeding is not the best. There is a better technique called beam search, in which at every time step, we choose the top n words for that particular time step. And at every step, we actually keep the top, in this case, it's B words. This is a hyperparameter, this B here. It's a hyperparameter of the beam search. We always keep the top B options and we discard the one that are less probable. Let's have a look at the training now. As I promised, the training is much more easier with the transformer than with the, not easier, it's more fast. It's faster with the transformer compared to the recurrent neural network, and we hopefully want to do it only one pass. So we don't want to do a for loop like we did with the recurrent neural network, and I will show you how. Again, we want to do a translation task. So we have an English sentence, I love you very much, and we want to translate into Italian, ti amo molto. Hopefully you will also learn some Italian. And let's proceed further, and we have again our transformer. So the first thing we do is we prepare our English sentence, which is the input of the encoder. Again, we transform the sentence into input embedding, we add the position encoding, we feed it to the encoder, and then we will get some output exactly at this point. Let's visualize it. We feed it to the encoder, we get the output of the encoder. Now, here we can see that the output are shifted right. Now, what does it mean to shift right? We want the model, given this English sentence, to output this particular Italian sentence, but we need to prepend a start of sentence word. So basically, we are shifting right the outputs, and we are shifting right here in this case means actually prepend a start of sentence token to this sentence. Again, we prepare the input for the decoder, which means we convert this sentence into output embedding. We then we add the positional encoding to each position, and we apply the multi-masked multi-head attention, and we also use the output of the encoder, and we give it as a query and the keys to the decoder from this connection here. The decoder will produce one output, and then which will be mapped to the linear layer, and finally to the softmax. And finally, what we do is we have our target sentence, right? Which is ti amo molto. We want the model to map to this one, ti amo molto, end of sentence. This is also called the label or the target. What we do is we calculate finally the loss, the cross entropy loss between what we expect as output and what we actually get as output from the softmax. And all of this is done in one pass. We didn't do any, there is no other time step. This is the only time step you need to do for this particular translation task. So for this particular sentence that you want to translate into Italian in this particular way, you only need to do one pass. And the beautiful thing is that the multi-head attention is parallelized because, I mean, it's just a bunch of matrix multiplications that we are doing, and we are not doing any for loops like we did for the recurrent neural networks. So no matter how huge is the matrix, it can always be parallelized. I hope my video was clarificatory for all the aspects that are part of this amazing model that is the transformer. It took me a while also to get into all this, into all the details. I hope you got most of the understanding that I wanted to convey. If there is something that is not clear, please let me know in this comment section. So as I said, this all happens in one time step. So the training is really, that's the game changer for the transformer compared to other models before. You train it very fast, and you can train it huge models that are have a very long sequence length, and that's why we have GPT, and that's why we had BERT, and then why we have ChatGPT now, etc. Thank you for watching, guys, and don't forget to subscribe for more amazing content on AI and machine learning. I hope to see you soon, and I hope you are eager to learn as much as I am. Thank you for watching.